everyone. I'm very happy that you are here. Just some announcement beforehand. I think you really make most use out of this workshop if you also have R and RStudio downloaded on your laptop. And if you haven't done so, then please do it now. In the chat, you will find places where you can download R and RStudio and install them on your computer. And then hopefully you can do that in the intro, so you'll be done in time, so you can just go along. Because how I envision that this workshop will go is that we will all start coding. We will all use code that I have provided for you on a website. The link I will also show you soon. And then, it's better to do it like this. Then we'll all copy code from this website and put it into R, so we are all simultaneously creating graphs and maybe seeing the problems that arise. All right, now just a very brief intro. We are going to use R, and in particular, we are going to use ggplot2. That is a package that is developed for R that helps in visualizing. And with only limited lines of code, so here we see just one line of code. You don't have to copy this one yet. We can make a graph that is already reasonably pretty. One might say even better than the standard in many fields currently. But of course, we'll learn how to improve this even more. Now, why are we interested in graphs? Just a reminder, you are all here because you want to learn graphs, so I guess you have a good idea. But graphs can change the world, firstly. So here's a famous visualization from Florence Nightingale. And I won't really go into it, but what Nightingale did was she was one of the first to beautifully visualize deaths in a war. And she actually, with this visualization, managed to convince generals that army hospitals are really important, because she showed that more people die from diarrhea, infections from wounds, and all that than from actual bullet wounds in war and actual war-inflicted wounds. So people were more likely to die from the consequences and from bad hygiene than from violence, so to say. So graphs are really important in that they can change policy, of course. We also know that graphs are important because of this Anscombe's quartet that's already very old now. And the point of these 4 graphs is that they have identical regression estimates, and they also have identical summary measures. So the averages for the X and Y and the standard deviations for the X and Y variables are all the same for these 4 different panels. But the pattern in the data is completely different. So of course, if we see those 4 graphs, then we know that this similar regression coefficient is not a very accurate representation of the underlying mechanism. So if we think about a correlation, we probably think about the top left panel. You know, there's some, for instance, positive line, and there's some variation around it. But it could also be that there is a curvilinear perfect pattern, such as in the right top panel. But if we just fit a linear slope to that, then we, of course, will not find this curvilinear pattern. Another one might be that you have some outlier, or maybe some measurement error, where you have a perfect linear relationship in the bottom left panel, except for one data point. And another case is where you have absolutely no pattern between X and Y, yet you find a very strong correlation because of this one outlier. So really, it is important to visualize your data, perhaps even more so than doing fancy analysis. And Anscombe actually wanted to combat this idea that statistical models are exact and the truth, and that showing the raw data is sort of guesswork. And he actually flipped that around. We have come far from Anscombe's quartet, because now we have the data source dozen. So what this shows is, again, it started out with a dinosaur, and then all these different visualizations you now see, all these different graphs, again, have the same relationship between X and Y, and they have the same variables, same averages and standard deviations. Now, to drive the point home, why we need to make graphs and why it's always good to show your data is that here we find a bar chart. So this where it says Weisgerber et al. You see these two bars. That is a very popular choice of plot in scientific literature. But this bar chart with these standard errors can actually mean many different patterns. It could mean something like B in symmetric, what we typically think. There is an average with some variation. However, it might also be driven by one outlier. And there might also be bimodal distributions that underlie these averages. Or in case of these standard errors, there might be a very unequal n between these groups. And as a last point to convince you that graphs are important, here we have another bar chart with almost identical averages and identical confidence intervals. And even if you make a box plot out of this, they look more or less similar. But when you make histograms and show the actual distributions, you see that they are very different. And that's why there was a Kickstarter campaign that said, friends don't let friends make bar plots. So don't make bar plots. And yet we will make many bar plots today. Okay, so what does this all have to do with open science? Good question. Well, typically the objectives of visualizations are framed into exploring the contents of the data. Maybe there's a structure in your data, also about checking the assumptions of your statistical models, and importantly, communicating your results. And I think that we should add as a major objective is that good visualizations allow close scrutiny by your reviewers or by your peers in the community. So the aim of a graph should also be that you give the reader insight into your data to your best ability, basically. So that means don't only show averages, but try and show as much of the underlying distributions as possible, or even the raw data as possible, because you want to be able to, that the reader can pick up these things. And there's just one example I would like to give you. Here there's a simple slopes graph that is also very common in the psychological literature on financial risk-taking, where you see this cross. And that's fine. They found an interaction, which is why they made a simple slope graph, which is a graph of statistical estimates. But why would you present that? Why you could also actually show the raw data. So on the right-hand side, I made the same graph in using the raw data because they provided their data, which is great. And the nice thing is with the right graph that you can now ask more questions. You can say, okay, well, apparently on the y-axis is financial risk-taking. There were many, many people who were not really engaging in financial risk-taking. Also, there's a scale for physical attractiveness. Okay, there are many people considered highly attractive, and so on. So this data allows you to much more closely scrutinize perhaps the analysis. All right. There are also a bunch of reasons why we're going to use R, but I guess the best reason is that it's free and open source and developing and great. Okay, now let's go into let's go to ggplot, a quick overview. So let's now start on what does ggplot do and what is the sort of the standard grammar that it will use. Before doing so, I hope everyone has our studio open now and are installed, so they can join us. From now on, I suggest that you just copy the code that you see, and then you copy it into your RStudio screen. If you have problems already at this stage, maybe you can use the chat, so Vera can help you out, and otherwise put your microphone on or share your screen, and I might be able to help you out. Let me also quickly say that before we start, you need to install ggplot2. So you need to run the package install packages ggplot2 into your R thingy. I will not do that because I already have a ggplot downloaded. Okay. Now, before we continue, we are going to make use of ggplot2, which is a package that is written by somebody. And if we want to make use of that package, and the package is in essence a collection of functions that we can use, we should tell R or our studio that we are going to make use of this package. So what we are going to do is we are going to copy library ggplot2. So you can just copy this text, or you can push this button here, and then we will run it into our console. And hopefully that all works for you. If it doesn't work, it's probably because you haven't got ggplot2 installed. Now, the typical ggplot code that you will see looks a bit like the following. You always start with ggplot. You are opening a ggplot object, and then the first thing you do is you specify your data set. In this case, it's called your_data. And then we have to define, we see something that refers to aesthetics, where we say which variables we want to visualize. So here we say x is the x variable, and this x_ variable, that is the name of a variable that should exist in the data frame or your data set that you have specified here. And the same thing, this y_ variable should live in this your data. And here with this geom_point, we're saying, okay, I want to make points. So this code will give us a scatter plot. So now let's try and run all that code. So this doesn't work. Why doesn't this work? Who has an idea?
Because you didn't specify data.
Right. Right. More formally, more specifically, that's exactly right. There is no your_data in our environment. It doesn't know. We're referring to something called your_data, but your data does not live in our environment. So we can't actually run that code. And later we will obviously make use of the data set. Now, just to follow up on this, if we somehow, we often see this x and y variable, but what we will also often see is a specification of a color. And again, you can specify, let's say, the color of the dots by another variable, and it's called group_variable, and that should then also live in your_data. So this code is fairly human readable, I would say. Okay.
Sorry to interrupt you. We also have a question in the chat by Natalia.
Yeah.
Who asks, what data is used?
Okay, great. We're going to do that right now. So we are going to make use of an inbuilt data set, and that data set is called MPG. Okay. And it is a very fascinating data set on cars. So if you copy this code, and if you run it in your R console, then I hope if you copied it and everything has gone right, then now in your right top corner in our studio, you have something in your global environment called MPG. Okay, this is your data set. And you can see MPG consists of several variables, manufacturer, model, displacement, year, and so on. So this is the data set that we'll use. So it is a data set on cars. So there are different car models, Audi, Volkswagen, and so on, and from what year they are, and also how fuel efficient they are. And this is the data set that we will work with most. Now, let's try and see if we can make ggplot work for us. So we are going to copy this code, our first scatterplot. Looks a bit funky in my Did everyone succeed?
Yeah.
Pretty good, right? We made our first ggplot. That's already impressive. So we're already, basically, this was the hardest part, that you have one graph, because now we only have to adapt this graph or other types of graphs. So major step already. Good. Now let's change the code. So who is daring to wanting to give an interpretation of this graph? So on the x-axis we have city, which means the fuel efficiency for a car while driving in a city, and a higher value means that it's more efficient. And highway means fuel efficiency on the while driving with your car on the highway. Anyone want to give an interpretation?
There is a positive correlation between the city and the highway.
Right, perfect. Cars that are fuel efficient while driving in the city are also fuel efficient while driving on the highway. That is a major conclusion. Yeah, no, that's not so exciting, of course, but it's good. Correct interpretation. Okay, so let's give these dots a different color. So what we're now going to do is say, okay, let's specify a color, and we are going to use a new variable called drv, and that drv is a variable that lives in MPG, and it says something about whether it's a fore, a front, or a rear wheel drive. So let's all run that code. Okay, pretty cool. Now, we can make use of many different geom functions, and that will create different types of graphs. So let's now run this next code where it says geom count instead of geom point. So who is wanting to make a suggestion of what has been done here in this graph?
So the number of cases represent the size of the dots.
Exactly, exactly. So this is a bubble plot, and indeed, the size of the bubble represents how many cases there are. And this actually shows that one of our earlier graphs wasn't actually very good, because we apparently had many overlapping data points. So this was a problematic graph, and then bubble plot would be better. Now, a nice thing with ggplot is that you can add so-called layers. So we had, let's say, our first layer. Now we're going back to the scatterplot using geom point, but now we're going to add another layer. We're saying, okay, we are going to add a layer called geom smooth, and that will add a regression line to it. And R is also so kind as to tell us that it is a regression line using the lowest method and what formula it has used. Okay. Now, then with R, you can change all sorts of things. So I've created here a graph that is not very pretty, but I wanted to show you some of the different things that you can change. We can change the size of the dots. We can change the shape of the dots. We can make them see-through with this alpha is 0.5. We can specify a different method for the regression line with saying method is LM, standing for linear model, for instance. We can change the color palette, and we can, of course, specify labels. And as you see, the code is, again, reasonably human readable, that for most of the things, you might have an idea what they would be doing. Maybe not the alpha 0.5, but now you know that that refers to the see-through of these things. Okay, so we had a very quick overview. We actually made it work, so that's great. So now let's take a step back and do a little bit of theory of ggplot. So the GG in ggplot stands for the grammar of graphics, and let me just read it out for you. And this GG grammar of graphics describes the deep features that underlie all statistical graphics. And well, that doesn't help us in any way. But Wickham, the author of the ggplot package, writes, in brief, the grammar tells us that a statistical graphic is a mapping from data to aesthetic attributes of geometric objects. So you see that this mapping is in sort of code form, and this AES is in code form, and this geom also is in code form, because those are terms that always come back in ggplot. So again, we are mapping particular data to geometric objects, right? So we are mapping, let's say, two variables to, let's say, a square. We are making a scatter plot, and we're making those squares. So we're making a mapping of those two variables onto a geometric object that could be a square. And we can also we also map these variables to aesthetic attributes to these geometric objects. So what that means is that these squares, they have a location in space. So those are the x and y coordinates. And that's, of course, in sort of aesthetic attribute where it is placed on the coordinate system. But we can also change the shape, the size of that symbol, and the color, and so on. It actually doesn't really matter if you don't follow this, because the code is actually fairly more intuitive than my explanation just now. Okay, so given that we know that there is a sort of a mapping of variables to aesthetical attributes to geometric objects, now let's see how that is sort of how that comes back into this ggplot code. Now, remember that previously we have seen this line of code. What this is actually short for is that we have ggplot object, we have data, right? It is a mapping of data to aesthetical attributes of geometric objects. So we need to specify data. And then we are going to map data. So the data is the variable city that lives in MPG, the variable highway that lives in MPG, and the variable DRV that lives in MPG. And those variables in some way are coded into aesthetical attributes of our geom, and we have chosen for a geom point. And we are just using a normal Cartesian coordinate system. That is the default in R. So again, this line of code actually stands for this entire thing. Okay, so now you know what ggplot stands for. Here's another reminder of this process from Kieran Healy's book, Data Visualization for Social Sciences. It is freely available, and it's a very good book with very nice visualizations. Okay. The great thing about ggplot is that it works in layers, so you can add as many layers as you want. So first we define a ggplot object, and we can then say, okay, I want a geom point, a geom smooth. We could also add a geom count here and many other layers if we would want to. Now you might ask, what kind of geoms are available to me? Well, there is a lovely ggplot cheat sheet that you can download. There's a link to it here. And there you can see all the geoms that exist in ggplot. So those are the geom functions that come standard with the ggplot package. Okay, so that was for our theory. Now let's delve into actual graph making. Everyone still with me? Or did half already go home? All good?
Yeah.
Okay. Okay. Thank you. All right. Now, let us now continue by making many visualizations, but we'll divide it up into how we typically go through the research process. So first, often we want to make we want to visualize a distribution of a single variable. Then we maybe want to compare distributions. Following up, we often want to see some group statistics as well of those distributions. So we'll run through that process. So again, the first step that we typically want when we have a data set is looking at individual variables and see what their distribution is. And we can do that with the function of geom histogram. So let us make our first histogram. So we say, we're all going to copy this code. We are going to make a histogram of the variable city. And again, the variable measures the fuel efficiency from different car models while driving in a city. Now, we all get a warning here, if all goes well, that stat bin using bins is 30, pick better value with bin width. What would that mean? And how can we resolve this? All right. I have an idea. So a histogram is a type of visualization where you have a continuous variable and you divide that variable into equally distant bins. And then you're going to count how often data points in your data set fall into those bins. So for instance, here we have a bin. It's a bit unclear from how far to how far it goes, but there were apparently about 5 cases between, let's say, 8 and 9 that had a value of city between 8 and 9. And there were, let's say, 26 cases of, let's say, a value of city around 18. So okay, so that's what a histogram does. Now, which bin should we choose? That's of course an important point. Now we have ggplot, let that decide for us. Ggplot says, well, I have used 30 bins, but pick a better value with bin width. So don't leave it up to me, you should decide. So it also gives us a helpful suggestion how we should change that. So we can say, okay, let's do it better. I know that this city variable is an integer variable. That means that it only has round numbers. So it would be very sensible to use a bin width of 1. Because that would actually then be a normal counts of all the values of city in the data set. So let's all run this code. And we get a histogram that looks very similar to the previous one, but it actually doesn't work. Isn't exactly the same. And here we can more clearly see that, okay, there are 5 values that have a value of 9. There are 20 values with a value of 11, and so on. And of course, a priori, you have to decide on what is a useful bin width. But of course, you can play with it. We could also say what would happen if we would do a bin width of 5. Then, of course, we would lose some of the specificity. We can also say, okay, how about I make that bin width much thinner, and then we get these weird peaks. And the reason why we get these weird peaks is that our data is actually not at this level of specificity. So there is no number behind the comma in this data set. So we see these very thin bins, but we know that this bin just corresponds to the value of 9. Okay. Cool. So now I will run this line of code. Also, please do all run this code, and then we get a situation. So I wanted to incorporate another variable, namely drive, and now it doesn't work. So why didn't this work? Why doesn't this work? So the reason is that this geom histogram does all kinds of stuff in the background, but it does not expect a y variable. Because what the geom histogram does is it cuts up this one variable, and then it counts how many times certain bins occur. And that the number of times these bins occur, that is the y. That is the y variable. So so behind the scenes, basically, the geom histogram function is creating its own y variable, namely how high the bar should be. So if we specify a new variable, it simply has no idea what to do with them, particularly not if we specify it as a y variable in this case. Okay, let's try another one. So here we have the next function, and now we are going to use car models. And so this is a character variable that says what kind of model it is. So we run that, and then we again get this error message. It doesn't create a new graph. Why is that?
Because the car models are characters. So it's like actual names, and it wouldn't count anything, but only take the names. Exactly.
Exactly. So in this case, there is nothing to cut up. How would you cut up a word, basically? So a histogram is not the right way of visualizing this model. Of course, you could make a bar chart. You could make counts of how often these different models occur, but you don't do that through the geom histogram. Great. All right. Now, let's try and spice it up and tweak some aspects of this histogram. So let's say we want to make this orange. We want to make this histogram orange. So we're going to, again, visualize our city variable, and we run this code. We specify our own bin width. Very great. And we say color is orange. And then probably that's not what we had in mind, right? We had hoped maybe that the entire histogram would have been orange, but we might be able to deduce now that in the histogram, when you specify a color, it only refers to the lines outside the bars. Now, how would we be able to change what is inside this color? How can we change this fill? That is by using the function of fill. So let's just make that another color, blue, because we want very ugly combinations of colors here. And then we can clearly see that if we specify color, then this is sort of the border around a geometric object. And if we use the fill, then that concerns the inside of the geometric object. Right. Ugly. We can, of course, also say, okay, I don't want any fill. I want them to make them see-through. So how would we be able to do that? Well, then we can specify the fill with an NA, which is the not available, and that is a missing value in R. So if we use fill as NA, then you can clearly see that it's see-through. We only have these orange outside bars. In the same way, you could do that for color. You can say, okay, I don't want this border to have a color, and then we see the reverse pattern that only the fill is colored in. All right. Now, just some more aspects we could change in this histogram. We run this, and I really tried to make something monstrous here. We can change the bin width. We already knew that. We change the color of the outside of these bars with purple. Color is purple. With the inside, fill is yellow. The alpha is 0.5. Again, this alpha refers to see-through. So if you look very closely, you still see the white lines behind the yellow. We can specify the line type, dashed. So you can see that the purple lines are now dashed. And we've actually made the lines surrounding these bars a bit smaller than standard with 0.5. And the nice thing is that some of these parameters, these ones, come back in many different geoms. So you know that if you have different, you are doing a scatterplot or something, then chances are that you can also make use of this exact code. Right. So let's move on to a different form of visualizing one single distribution of one variable. And now we are just going to make a density plot. So instead of saying geom histogram, we're now saying, okay, geom density. And we are doing this for the city variable. And now we have created a density plot of our distribution. And the different thing about the density plot is that the area under this curve is 1, and it doesn't work particularly well for this situation. Density plots do not work with bin widths in the same way that histograms do. So in histogram, you have these bin widths, which determine in how many pieces this variable is cut and how wide these different intervals are. Density plot uses a bit of a different technique, and they use bandwidth instead of bin width. And you can also specify that in the same way as you did with the bin width to make different density plots. And again, all the area underneath this curve is sums up to 1. Let's just try a little different bandwidth. So those are our density plots. Density plots are not really useful when you're trying to visualize one single variable, I guess, but they might come in handy when we want to compare distributions, as we'll see later. Now, let's try and tweak this density plot. And if we do that, we see that actually all this we've seen before, right? All this code, all these different little features that we are tweaking, that's the same as we did for the histogram. So it's very nice that we can just copy that previous code into here, and then we can create a similar ugly density plot. All right, so we've now managed to visualize a single distribution. Now let's move on and say, okay, now we know we have one distribution, but I want to compare different distributions. I want to compare men and women or something like this, or I want to compare the different car models and their distribution on how fuel efficient they are. And we'll see many versions of that. So again, let's start with our histogram. Let's say, okay, we are going to compare distributions, and I know about the histogram. I also know that we can specify a bin width. And now I want this for 3 different drives. So this DRV variable again stands for front, rear, or 4-wheel drive. So let's specify this as a color. And then we get this graph. So what has happened? What has happened, and is this nice? Is this what we wanted? Who has something to say about this graph?
It's a bit hard to compare all the distributions because of the overlap.
Right. Exactly. So what do you think it has done?
Layers all the graphs over each other and provide an outline.
Yeah. Yeah. So it has stacked all these bars. So it has counted all these things. So here it counted that there are 4 4-wheel drives. Apparently there are 5 4-wheel drives that have a fuel efficiency of 9. That is very small. There are also 5 rear-wheel drives that have a value of 11. There's 1 front-wheel drive here, and so on. So it has stacked these bars. So I would say that might not be the best way here. And furthermore, it is also visually not very clear that we only have the surrounding lines and that still the inside is black. But luckily, we know how to change that, because we know that we could change this fill as well. So now let's say, okay, I want to make both of these things corresponding to this drive variable. And then we get the following graph. Still, we have the problem that that all these bars are stacked on top of each other. So it might not be the best way, but still the differences are more clear than in a previous graph. Now, it is good to realize that perhaps we didn't want a stack. Maybe we just wanted these histograms that they're overlain, but that they all start at 0. But this is probably not what we want. Now, it's good to realize what the actual defaults is when you are running geohistogram. So when you are running this code here, what we have just all ran, what it actually says is geom histogram, bin-width is 1, that's what we specified. Position is stack, that's the default. Right? So if I run this code now, it will give me the identical graph as before. But this is very good to know, because we know now that this is the default argument that is given to geom histogram. And we also realize position is stack. That probably says something about these different stacks of counts on top of each other. So probably we can change this stack into something else. And indeed we can. We can choose it. We can replace it by dodge, fill, and identity. So now let's look at what they are doing. Now we run the position is dodge. And we have something that is already perhaps more clear. So what has happened here?
The columns are now next to each other, so you can compare them a little bit better.
Exactly. So per bin, there are 3 counts. And yeah, that works already a bit better, I guess, than the previous one.
Yeah, but it's still confusing, right?
A little bit. Because, yeah, it's still, I also would not say this is an ideal situation. But if you're really careful, if you're really scrutinizing the graph, then you can see all the counts and you can compare them very closely, but it is not ideal, I would say. Now, an alternative to this position. So now we had stack and dodge, and now we have fill. Do that. We get something funky like this artwork, like Mondrian or something.
Wow.
So what it has now done is that it has said, okay, I'm going to fill these bars up so that they all stack to 1 or 100%. And then I'll show the relative counts, as it were, for these different things. So this gives yet another insight. What is very unfortunate here is that you miss some things on sample size here. Okay, now let's change to the last one. So we had dodge, we had stack, we had fill, and now we are doing position identity. And that might be already a bit more closer to what we were after. So we see now what it has done is that it has just put all the histograms starting at 0. So how can we improve this graph? What would be an easy fix to improve this graph a bit? Or differently said, what might be problematic about this graph?
Yeah, because we don't see for every bin what is happening with every category.
Perfect, exactly. So what is red doing here? Are there no values of red, or are they just as high as green or whatever? And is there blue over here or not? So we can fix that by making it see-through. And the see-through we could specify with this alpha, as we've seen before. So now we run this code, we say alpha 0.5, and we will make all these fills see-through, and then we have something that is, I guess, something we were hoping for when we wanted to compare distributions through histograms. But again, it takes some effort to really see differences.
And Gert, what does the alpha mean? Is it the level of transparency, or?
Yes. So alpha is transparency. If you make it 1, then it is completely non-transparent, so it's completely opaque. Yeah. If you make it 0, it will be. Let's try. If we make it 0, then it will be completely see-through, or you will not see anything. Alrighty. Now, just so let's move on from histograms and go to something that looks very much like a histogram, the so-called frequency polygon. We run this code. So this first bit is the same as we did for the histogram, but not rather than saying geom histogram, we say geom frec poly, bin width is 1. And if we do that, we get something like this. So what is this? What's it visualizing?
I think it's just the same, but it's drawing a line between the ends of each column of the histogram.
Yeah, good. So very good. Now, now also this geom frec poly has this position is, right, that we also as a default. So what position is default would this frequency polygon have? So we saw in the histogram that the default of histogram was position is stack. Okay, so this position is stack meant that the default for histogram is doing all those counts and put these bars on top of each other. And we saw that we could also use position is dodge, and we could also use position as identity, which made all these histograms basically on the ground starting at 0. So this frequency polygon looks very much like this one. Actually, it's the exact same data. So what would you guess would be the default position is argument here?
Yeah, that's identity then.
Exactly. Exactly. Exactly.
Yeah.
So that's the default position is identity. But again, you also realize then that you can also have then, you can also change that again. Okay, so very good. Yeah. One more thing. This geom frequency polygon, it doesn't have a fill. It is just a line. So if we would have removed this fill is drive from our code, then we would have gotten the exact same graph because this geometric doesn't expect a fill. All right. Now, important bit, the difference between mapping and setting color. So let's see those differences. So again, mapping was that you mapped data to particular aesthetical attributes. So let's first set colors. We're going to set colors of our graphs. So now let's run this earlier graph and we set the color by saying fill is orange. Right, and then we have this orange histogram. This should all be very intuitive to you now. And we could also map colors, right? And map colors is when we added this mapping of data within our aesthetics. And we said, okay, this fill should have the color of the 3 different drives, and drive is a variable that is in our dataset MPG. Good. What happens when we set a color using a variable? So now we run this following code. So instead of saying fill is orange, we say fill is DRV. And then we get this error message. So in essence, only when you define this mapping of data to aesthetical attributes will it look for this variable into this MPG dataset. So only everything that is within aesthetics will be looked for in this MPG dataset. So here we say fill is drive, but it will not look for drive in this MPG dataset. But even if it were, here what we previously seen is that it said fill is orange, right? And drive is fore and front and rear. So even then it would not work. So when you set a color, you cannot make use of a variable, and also it will not look for this object into this MPG.
Could you also not define it like saying MPG and then the $sign variable drive?
Good, let's try that. So let's see, we do that.
Oh, nope.
Right, so we said here, so what we did, we explicitly said, okay, look for this DRV in this data set. And that is when we set colors, it just expects names of colors. So if we then give it a variable with 3 categories, it doesn't know anything. So everyone with me? Right, so again, I'll show the situation that it does work. Now I'll pick another color, purple. If you say fill is color name here, then it would work. But here it looks like we want to map a variable, but we can only do that. We can only map variables within this aesthetics bit. Okay, let's see now. Let's see if I have my own color. Can you see what I'm writing here? In the top left corner, in the top left.
Yeah, I think it depends on how large screen you have. I have a quite small laptop screen.
So I'm writing here, own color is blue.
Yeah.
Yeah, so everyone sees now on the screen that I have some object called own color and the value there is blue. Everyone with me?
Yep.
Yes.
Okay. Now, if I would do this, what I've now said is, okay, and the fill is, and it expects the name of a color. And we can do that here. We could have written, say, blue, but you can also specify an object name, and then it looks for it in the environment. It doesn't look for it in the data set, but it looks in the environment. It goes into the environment, and there, the value of this object is the word blue, and that is a color. Okay? Okay. So this is, doesn't matter if you don't really understand this yet, but I will tell you that this probably will be a point of frustration for you in the future when you're trying to change colors and you mix up setting and mapping. So let's now try the other one. Let's now say, okay, we are going to set a variable. So we're going to use, let's say, for instance, orange, the name orange, but we are going to do that within the mapping of aesthetical attributes. So now we say, okay, X is city, as we've seen before, and we saw that it worked if it said here fill is DRV, but now we do fill is orange. Okay, and we run. Very nice now that we actually have a graph, but that is probably not orange. I'm pretty sure it's not orange. And it also has made a legend for us all of a sudden. What happened?
I think is it the default color?
Yes, yes. So let's make it blue. Wait, let's change orange to blue, and then we'll have the exact same graph. So why did that happen? I will tell you. If we specify something in quotes here, it won't look for it in the data set. But instead, what it will now assume is that all the data points that you have, all the different city variables, all the values, all the different city values, they belong to the category called orange or blue or banana, whatever. So you did not specify a color. You just said all these different city values, they belong to this category called orange, right? So again, I'm just now going to make it a banana just so that you can see that it doesn't matter what it says there. So banana, and it has used that information to say, okay, all these city variables, they belong to one group, and that group is called banana or orange or whatever. And I will give it the default first color that I would typically give to groups if I only have one group, and that is reddish. And that is now the color of your graph. Understand? Sort of?
Yep.
This is tricky stuff, but again, let me tell you, when you are mucking about with your graphs, then the difference between mapping and setting colors will be very important, because I think you typically want to change colors and then you might do it in the wrong part of the code. Okay, good. Yeah.
How do you change the default color? So it's red, blue, and green. Not very friendly. How do we change that?
Excellent question. So if you go to the left column, all the way to the left column, and then there's this section, other useful stuff, there are all these sections on if you want to tweak certain aspects of your graph. So you go to the color section, there are many examples of how you can change the colors of your graphs. Right. So if we go through them, also with gradient scales and all that sort of stuff, you can make use of existing color sets that are much nicer than the defaults. Here are some names of different color palettes. These are also very friendly for people who can't see all colors. There are some nice Rijksmuseum palettes and all that stuff, right? So in the section on colors, you will be able to find exactly what you need. Okay, so let's continue. Yes, we were comparing distributions. We saw histograms, but we can also compare distributions with density plots. So let's see. We run this code. We get these nice 3 little mountains. This works well, but it's also quite nice if we can fill them. We know how to do that because we know how to map the variable drive to the fill. And then we get this really nice mountain range, and it looks very pretty, but of course we might want to see what's going on underneath this. So we can set the alpha to 0.5 to make it see-through. And then we can have a nice comparison of these different graphs. Okay, I went through that very quickly. I hope that's okay. Now, remember those shapes, we will now show them again, but now through violin plots that are increasing in popularity. So we'll do the same thing now. But now we're saying, okay, on the x-axis, I want these different drive variables. On the y-axis, I'm going to make these sort of density plots, but I will make them into violins. So that means that they are symmetrical on both sides. On both sides is this same distribution, basically. And then we have a violin plot. And this perhaps allows a bit better of a comparison between the distributions. Of course, we can also fill these different violins with the color. So we know how to do that, right? Because we know we can map the variable drive to the fill, and then we get something like this. Yeah. And this looks, I think this one with color looks nicer than this top graph, but in reality, these colors are very redundant, right? Because they don't code for anything that we didn't already know, because the colors correspond to what is on the x-axis. So I guess purists would say that this is not good because you're confusing readers, because now they're looking at colors and they might think, what are these colors signifying and that kind of stuff. But no, it's also nice to look at nice colors. Okay, just a little bit of a detour here. Often we let our statistical software choose the ordering of the axis for us. And that typically will be done on alphabetical order. And why would we want that? Right? That's hardly ever a good solution. It might be a much better solution to change them on the order of some statistic. So now let's try and change the order of this x-axis on the basis of the median value of the score of city. What we then can do is say, okay, I want to reorder the drive variable that was on the x-axis. And on the basis of what should I reorder those factor levels? Well, I want you to reorder them on the median of the variable city. So this reorder will reorder these levels, these 3 different levels of this factor, on the basis of the median of these 3 groups and the median of the variable city. So as you might imagine, I could also do the mean here, or maybe the standard deviation, all those kind of things. But now we choose the median, and then we see that these 3 violins are plotted on the median rather than on alphabet. Yeah, no, I'll just use some other examples, but let's go on. We can also set our own order. This is also something that you might want to do frequently. And I just want to show you, because it's good to have control over what you put on the x-axis and y-axis. So rather than doing it, ordering it on the median or the mean, we also maybe sometimes have very specific reasons why we want to order something. So now I'll show you how to do this. In order to come up with a good order, we have to define a so-called vector with the names of all the levels that exist in a particular variable. Right now I have the variable class, and it consists of mid-size, minivan, SUV, pickup, subcompact, 2-seater, compact. And I want them in a particular order. I want mid-size first, minivan, then SUV, then pickup, and so on. I have to store this into an object, and I call the object order, but also here it could have said banana. And then I have to tell ggplot that I want to make use of this order. So what I can do is say, okay, ggplot, I want you to plot class, right, the variable class, but with this code, I change the levels of class in the order that I have specified here. So if I would have said banana here it would have said banana as well. And then we can do that, and we specified our own. Here I provide you a different way of doing that, but it's not. Oh yeah. Okay. Yeah. Everyone still with me? I'm speeding up a little bit just because I think we're not really learning fundamental new lessons, for instance here, but I just show you a variety of graphs that we can use. An undervalued way of showing distributions is by just providing scatter plots. But in this case, that might be very poor because there are so many overlapping data points. So what we can do is we can make use of jitter. So let's run this code. It says rather than geom point, say geom jitter. And we see this distribution of points in comparisons to one another. So what would be a disadvantage of this jitter? I'll tell you. But what this jitter does is it adds some random noise to all your data points. So to reduce this overlap. But of course, if you add random noise to your raw data, then what you're showing to people is not the raw data anymore, which is maybe a bit uncomfortable. But we can resolve that situation in this case if we would only let it vary a little bit into this dimension, because we still know it will be four-wheel drive, but we don't vary it into the Y dimension, then this situation would be resolved.
So you only see small deviations horizontally.
Exactly.
Not vertical, so
exactly.
That stays at the same place.
Exactly. And we can do that by saying width is, well, whatever. And in this case, we want the jitter in the height. So the random deviations in height, we don't want them to exist. And then we get something like this. All right. We could also do bubble plots to compare with the geom count. We've seen that one before, so I won't run that code now. And of course, the very popular choice, and that's not really showing the underlying data, but those are box plots. And there's also a specific function for that. Now, my suggestion would be to you, in general, if you visualize your data, try and do as many variants of your data as possible, and that it still is readable and visible for the reader. So why would you restrict yourself only to one situation? Why would you only show a box plot or only the raw data? So for instance, why not you combine? Why not say, okay, I'm going to show you the violin plot that gives some impression on the distribution of the underlying data points, but that doesn't tell you anything about sample size, so I want something else. So I can do this bubble plot, for instance. Or in the case of these box plots, sure, show the box plots because it's good to know where the bulk of the data lie, but also why don't you just show the raw data as well? So that would be a suggestion I would have for you. And just very quickly before we start on an assignment, I want to show you some nifty extension packages that also exist to compare distribution. So here we have, and I will run through them. I won't run them. We have a package called ggriches. That is an extension package to ggplot that allows you to make these kinds of nice density plots where there's the focus on the comparison, on the comparisons of the distributions. There's a function called gghalves that basically is designed because of the point I just said. Like, why would you only show one geom? Why don't you show many more? So what we can do with that is saying, okay, I want one half to be a violin plot, and I want the other half to be a box plot. Well, that looks a bit funky here. So let's do another version. We can do a half a violin plot, and we can do Scatterplot. And let's flip it on its side, and then we have a cloud and rain plot, right? So this is the distribution, and these are the raw data points. And there are also another nifty things like a CNAP plot, where you actually have the density, but the density is made up by some jitter of data points. So that works well, for instance, if you combine it with the violin plot. Cool. So we've seen many cool things. Okay, let's say I am taking a bit longer than I had planned to, but let's take, let's say, 10 minutes to do an assignment. And also, if you need a break, that's also fine, or if you want to ask different questions. But let's see if we can sort of consolidate some of the things we learned and try it out on a new data set. So we are going to use data on temperature in the Netherlands. So it's data from 1901 to 2018. So you can read in the data by running this code, and there will be something in your global environment called data. You can see what it looks like by writing head data. And if you want, you can get some summary of the data. And let's try and compare the distributions of the temperature of the different months. Yeah, let's just try that. And if you are able to try to change some colors, maybe you want to think about reordering the x-axis in a more sensible way. Maybe you want to change the legends. So I'm here for you on the chat for any help. And yeah, let's do that for 8 minutes. So I'll do it here. It's a long bit of code, and I'll show. Then you have something like this.
Wow.
Damn. So now we go on to group statistics, and this is often we want to show averages of distributions in our plots, and sometimes we want that because if we have many data points, then showing the actual raw data might not help really, and then showing people averages or even averages and box plots would be a good way. But of course, we have to do something new now. Namely, we have to, from the data, we have to create something new, and that is then being displayed. Luckily, ggplot allows these kind of functions as well. And it's good to know that what then happens in the background is you have your raw data over here. Then your geom function or your stat function does something that creates a new data set. And that data set is then used for your visualization. So let's see. We want to plot the different manufacturers, so Audi, Ford, and so on the variable fuel efficiency in the city. And we want to show the mean. The bars, that means that are reflected by bars for all these manufacturers. And then we run this code. We're specifying that within our geom bar function, which is a new geom we've seen, that we want to create a summary stat, and which function we want to use is the mean. Of course, we can also use another function here, median, or maybe even our own function. But this is how you create a bar plot with the mean. Now, it works very similar when we don't want bars, but we want perhaps dots or points. So we do the exact same plot, but instead of saying geom bar, we now do geom point. And we run this graph and we get this, these dots. Easy. course, it's not easy that this is stat is summary, fun is mean. You had to remember that, or of course you don't remember that. You always look it up either on this website or you Google it, and then you can make mean plots easily. Typically, we don't only want to show the means, we also want to add error bars, and also that there exists a geom error bar for that purpose. So here, this is what we've seen before. This creates our bar chart with the means for the different manufacturers. And here we add another layer, so that is placed on top with an error bar. And again, we have to make use of this stat is summary. And now we have to say, okay, if we run this, then we are creating standard error bars on top of the mean. So clearly, this is something you couldn't have come up with yourself, but this means this is one argument, and this is a function that exists in ggplot that creates the standard error of the mean. So if we run this code, we see a plot that is, yeah, nice-ish, I guess.
Gert?
Yeah.
Does the geom error bar also works with the point plot? So if you would say geom error point, would you then get a standard error around each dot?
Yeah, good question. I didn't think of it this way. Actually, you can do exactly the same code as before, but then you just have to make a geom point. So this error bar here does not refer to this bar in any way. It just means these black things. So what you see here, this is exactly the same thing, but then now we set geom point here. Okay, great question. Now what we have plotted here is just the standard error of the mean, and often we want to change this to a 95% confidence interval. Mostly that means that you multiply your standard error by a z-score of 1.96. How do we do that? Well, we can do that by passing on arguments to this function, and we have a multiplier of 1.96. Again, this is just code that you have to look up when you want to do it yourself, and then you can make error bars that are 95% confidence interval. We can also do it with our own functions, but I'll skip that for now because of time. And here's your question, Vera. We can also do this for point plots in the exact same way. Right, so we have now let ggplot do everything for us and calculate everything for us. Of course, what I said before, we typically, now the default is that the x-axis is ordered on alphabet. That is fine, but maybe that's not what you're most interested in. So let's try and order these on the mean, and also change some of the aesthetic features, and then we get a plot like this, and that already seems pretty nice. So you can immediately see that Lincoln is the most fuel-inefficient car, and Honda's produce some of the most fuel-efficient cars. Okay. Well, I already said I'm not a fan of these plots because they hide the underlying data. So I would say it's good practice to also try and see if you can show some of the raw data, and we can do that. So we can add, for instance, geom jitter. If we add geom jitter to it, we see these blue data points. I've also changed some other aesthetical features. So I removed the top here of these bars. I've changed the text labels. I've given them different x-axis and y-axis labels and a different theme. So you see how that works. And this should also work on your computer. Okay, I guess, okay, good. So let's move on. Doesn't really matter what comes next. So now we've let ggplot do everything for us, right? We had ggplot create the bars and calculate the means and calculate the standard errors and that sort of stuff. But maybe we want to have a little bit more control, and we want to create these data sets ourselves. We want to create the averages ourselves and the standard errors and the confidence intervals ourselves, and then put that into ggplot rather than having ggplot do it for us. So we are going to try and do that. But before we do that, we have to learn something about transforming our data. Now, luckily, with this package called dplayer, we have a fairly intuitive syntax of how we can do that. So first of all you need to install this dplayer package, please. It might take some time, hopefully not too long. And then load this dplayer package. And then we are going to focus on 6 functions, and I will go through them very, very quickly because of time interest. There is a function called select that selects the variables of the data frame that you will be using. We're using filter, which allows you to select cases or rows. We are using mutate, which allows you to create new variables. Case when allows you to create different if-then statements. Summarize your data, summarize your variables into new variables. And that is often useful with group by if you have different groups in your data. So what you will also see is this very weird symbol here, the pipe, right? This percentage sign, greater than sign, and then this percentage sign is called the pipe. And what is very nice about the pipe is that you can read it as a normal sentence. So you go from left to right. So the pipe means, and then we are going to do this. Then we send the data frame to the following function. Give an example, if this all sounds very esoteric to you. We have our data set, MPG. We then send that to the following function, right? MPG, we put it through the pipe, send it to the function select, and we select manufacturer, city, and class. And what it has done is it has selected the only 3 variables, manufacturer, city, and class, that exist in MPG. Okay? Another example, we have MPG. We are now sending MPG, the data set, to this following function select. And we say, okay, we want all variables except minus trans, minus DRV. And then we have a data set that has all these variables except for minus trans and minus DRV. Okay? Is that clear so far? Okay, I guess yes. We can do the same with filter. So we can say MPG, let's send the data set through the pipe to the following function, filter, manufacturer is Audi. So now we have said, from all cases in MPG, I only want the cases for which manufacturer equals Audi. So as you can see in the resulting data set, they're only Audis. So we use that by that filter. Alternatively, let's say we only want fuel efficient car. We say, okay, our data set, we send that to the function filter, and we only want cars that have a value more than 20 miles per gallon. Okay, going through it fairly quickly. R has sort of the usual operators and Boolean operators. So a greater than sign, greater or equal, smaller than, smaller or equal. This means equal to, so 2 equal signs, and not equal to means exclamation mark equal sign. And you have these Boolean operators. The ampersand stands for and, a vertical dash stands for or, and an exclamation mark means not. And with these operators, we can combine logical statements. So again, we have this MPG. We send that data set to the following function filter. And what do we want to filter? We want to have all manufacturers, all Audi cars, only Audis, where the manufacturer makes Audis. And it must be fuel efficient cars. So that have a city variable value higher than 20. And then we see there are only 2 Audis that suffice this condition. And with the exclamation mark, we can do the reverse. So let's say we only look at fuel inefficient cars. We say, okay, send this data set to this function filter, equate manufacturer to Audi, and earlier we said we only want fuel efficient cars, but now say, okay, this entire condition must not be true. So we're looking for cars with a city variable less than or equal to 20. So that's what you also could have written here, but I wanted to show you the use of this not logical math statement. Okay, let me just move on a little bit. Are we still? Is everyone okay with the pipe and this function? Does it still make sense to you all? Okay, good. So now we're going to create new variables. So we do that with this function called mutate. We are going to send our data set to this new function mutate, and we're going to create a new variable, which is the mean of fuel efficiency, I called it. You could have also said banana here. And what is that? That is the average of the city variable, which is fuel efficiency in the city, plus the fuel efficiency in the highway divided by 2. And what it returns is the entire data set plus an additional variable called mean FA, which would be the average of these two variables. And we can also do that we can also create new multiple variables in one go. So let's have an example here. We say MPG, we send that to mutate. What we are first going to do is we are going to transform our city variable from miles per gallons into kilometers per, into liters per kilometers to liter, sorry. And we are doing that for 2 of our variables, so the city one and the highway one. Then we are going to make the mean of these 2 variables. And then I'm making another variable, which is the rounded version of this variable, right? You can do many more sophisticated things, but just to show you that now, in one go, we create 4 new variables. And the nice thing is that you can already make use of variables that you have defined just beforehand. So you see here, this data frame is the entire data frame plus 4 new variables. Now, this is nice in combination with case when. So case when allows you to combine multiple if-else statements. So for instance, let's say this drive variable that we have seen that consisted of 3 variables, levels. How about we want to change them into 2 levels where we only have 4-wheel drive versus 2-wheel drives. What we can do is say, okay, I want a new variable called drive_bin. Case when, if drive equals front, then I want this new level to be called 2. If it is a rear wheel drive, then I also want it to be called 2. And only if DRV equals 4, then it should be a 4-wheel drive. And that will create a new variable that has only the levels 2 and 4. Okay, so finally and importantly, we have summarized, and this is an important distinction to make here. Mutate always adds another variable to your data frame, and it has the same number of cases as the number of rows in your data set. With summarize, you always summarize something into one value or into as many values as there are groups. So let me show you. Here we can summarize the mean. So we send MPG into the function summarize. Then we create a new variable called mean_city. And then we have a function mean of the city. So this will create a new data frame that only has one value, mean city. That is the average of this variable city. And we can also do that. We can define multiple variables. And now you think this is not really special, and you're right. But how this is very nice is in combination with group by. So we have MPG. We send that to the function group by manufacturer. And then we summarize, and then we define 4 variables. We want the sample size. We want the average of the variable. We want the standard deviation. And then we want the standard error. And if we do that, then we see that these 4 variables are here, and they are created for all the different manufacturers. Not bad, right?
Awesome. Also, okay, to make the summary tables.
Exactly. And this is clear, right? This is fairly clear code to read.
Just one question. If you use the summarize function, do I understand correctly that it always gives you back like a new data frame? So based on the data frame you give in this case, the MPG, it uses a new data set.
Yeah.
And how can I find, of course, I can, no, never mind. I can save this as a new data file.
Yes, exactly. Yeah. Now you can also use multiple grouping variables. So you say drive and year, and then it will group it for drive and year. But now the beautiful thing, and this is where it is all heading. With the pipe, you can do all these steps that we've seen in one call that is sort of fairly easy to read. So here we send the data frame MPG to the function select class, year, city, highway. So we select 4 variables. Then that data frame we send over to filter. We only want the cases where year is 2008. Then we want to create a new variable named blah, 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 which is some transformation of the data. Then we have that data set. We want to group that by the class of the car. And for all of these classes, we want to summarize it into these 4 variables. And you can do that in one call. And this is sort of readable. Also for people that don't know R, they still have an idea what is going on here. And then you have a data frame that you can use later for your graphs. Okay, so 10 minutes on this, but I do think it's very important because, as you've seen, the coding in R is fairly intuitive. And if you create your own data frames, that allows you much more flexibility in what kind of graphs you can make. So let us put all this power into action. So we've seen this bar chart previously, and we could create that. But now let's say we are going to create it ourselves. We are going to create the averages for all these manufacturers because we know how, and then we are going to visualize that. So let us do that by running this code. We send MPG to group by manufacturer, and then we calculate the mean for the city variables. But of course, we have to save it into an object called MPG means. So if we run that code, let's see what's going on. Oh, I have to do that, yeah. Library declare. If we run that code, we have a now in our global environment something called MPG means, and that is exactly all the averages for these different manufacturers. Does everyone have that?
Check.
All good? Okay. Okay, so now let's use our data set that we just created with the averages for all manufacturers, and let's use that into our ggplot. So we say, okay, we have ggplot. We want the MPG means. That's our new data set. And then we want the variable manufacturer and a variable called mean city. And then, as before, we wanted this G on bar. Now, this is important that you now understand what happens. So it gives us an error. Namely, stat count must not be used with a Y aesthetic. Why does this happen?
Isn't it the same that we had last time? That you can't specify the another variable because it's just counting? Yeah, exactly. So what this G on bar does under the hood, when you don't specify anything, is G on bar automatically makes a count out of everything. So what it actually does is, as default, it has stat is count. And it counts, for instance, the manufacturers itself. But then in that way, it doesn't expect a Y variable because it creates that Y variable itself. So how can we resolve this situation? Well, we have to tell it that it doesn't use stat is count, but we have to tell it to use the following: stat is identity. So when we say stat is identity, that means that we give the identity of the bars. We specify it ourselves, namely through this Y is mean city. Right? So if you run this, then we recreate our earlier graph. Great. Everyone has that? Yep.
Okay. Okay, now let's run through that. now let us also try to add error bars, right? So we've seen this code before, and now we are going to do it ourselves. For this, we have to create some more variables than only the average. So let's do this. We're going to send MPG. We're going to group by manufacturer. We're going to make all these variables, the average, standard deviation, sample size. Based on that, we can calculate the standard error. And then we can specify an upper and lower limit for the mean. So we've done that. We've created that data frame. And now let's give that information back to ggplot. So we know if we want to make the use of the bar, we had to specify the stat identity. And now in the geom error bar, we have to specify these lower limits ourselves. So we have to say the y-min is the lower limit. That is a variable that exists in our data frame that we just created. And upper limit is also a name of a variable that exists in our data frame. And so we've recreated it. Let's see what the point there is. Yeah. Okay. So this gives you actually a lot of power that you have. That you can create the data set yourself and the average and all the estimates you want, and then you can tell ggplot to actually use that data rather than to calculate for us. So I suggest, in the interest of time, we are going to the section visualizing two continuous variables, because there's still one trick I would really like you to learn. And again, I might be talking a bit more quickly than I typically do. All right, so we've seen this Scatterplot many times now, or a similar one. We have now two different variables. We have the Scatterplot. We know how to add color to that by specifying color and mapping a new variable to the aesthetic attributes. And we've seen this before. Now, what happens when I run the following code? So I want to use another different color variable, namely highway, and then we create this variable which has some sort of gradient. Why is that? Even though here we had three separate colors, remember, for the drive, we created three different colors. And here, all of a sudden, we have this color gradient. Why would that be?
Non-integer values?
Yeah, almost, because it's a continuous variable.
Yeah.
Yeah, it's not a character or a factor. It's a continuous variable, and that's why it will assume that it is a gradient thing. That sometimes can go wrong. So in this case, for instance, in the below case, we are going to specify year, and then we get this. We get this gradient, but still we see only this blue and light blue situation. What do you think can cause that? So the thing here is that we have just learned is that actually there are only two colors. That means that there are only 2 years. And in fact, there are only models from 1999 and from 2008. It's just two colors. And then we can question ourselves whether this gradient is really the ideal solution. So how can we solve that? Well, we can just specify, say, okay, treat this variable year that only has an integer of 1999 and 2008. Treat that as a character variable, and then we get the same plot as before, but now with more distinct colors. Okay. Now, let's say we want to add a regression line to our Scatterplot. We've seen how we could do that before through this geom smooth layer. Yeah, so if we run this code, we see the Scatterplot with a lowest best fitted line through it. And as you might have seen before, we might also say, okay, I don't want a lowest line, but a linear regression method. We can specify this with method. We can also get rid of this standard error bar, for instance, by saying SA is false. And we might want to change the color. So let's say here we change some features. And now we have a regression line that runs through our scatterplot. We might also have a situation, of course, where we run models and we want to use the estimates of those models to implement in Ggplot. I'll skip that for now. But what I've done here is run a linear regression myself, and then I add a line to this Ggplot. It's the blue dotted line, and you see it's the exact same as the Ggplot has calculated for us. Now here is a nice trick, and that's the last lesson I want to end with, is that you can also make these regression lines for different groups. And let's say we have these different data points, we give them different colors depending on the type of drive they are. And then when we add this smooth layer, when we add those regression lines, we see that it adds them for all the different groups, right? And it also only draws them in the variation that that group spans. So this looks quite nice, right? And it's that's a quite nifty trick. But it's also very important to learn that there is a certain inheritance now going on, because we have specified this color is drive, and this color of drive that happened to this geom points, and it also happened to the geom smooth. So this layer of aesthetics is inherited to all its children. So this AES will be placed into this geom point, but also into this geom smooth. So here I have written out many situations that all means the same thing as the code before, but it's important to realize that what we have defined over here, that will be sent down to its children below. And that's a very important lesson, because we don't always want that, right? Because maybe we wanted to have these different colors, but maybe we wanted to have the overall regression line and not these three regression lines split up. Or maybe we wanted both. We wanted and the overall regression line and these lines. And we can fix that by thinking about these inheritance issues. Let's see where we are. Let's see what would be the best. Yeah, and it's then good to realize that, again, we have these defaults. Sorry that I'm flipping through all the time, but it's good to realize that what happens is that there is an argument within all these different layers that says inherit.aes is true. So that says, you know, the standard is inherit all these features from your parent, so to say. So let me just give them a parting lesson. So we have this inherit.aes is true, and that basically lets you inherit all the features that are defined previously. But now, let's say if we specify, let's do a better example. When we say inherit AES is false, then we can have much more control over which features we want to be inherited and which not, and such that we are able to show a regression line for all these bunch of points, despite these points having different colors. So I'm sorry that it's a bit of a abrupt ending.
Yeah.
Just one more thing. Let me share the screen once more. You can also download these materials by using this button, and then you get this PDF version. And that PDF version is certainly not ideal, but you might want to do that. So again, thank you very much for joining. I'm sorry we had to rush a little bit in the end. And now I really have to go, and already somebody's opening the door. So,
Thank you so much.
Okay. Okay. Thank you all. Bye-bye.